Okay, so the last question, a tough moments question. I must admit, I really enjoyed this kind of question, and also I disagree with the solution which is given in the, so the solution page. And I want to talk through exactly why I disagree with it and exactly where I think their solution went wrong. But I think that they had absolutely the right idea. I think it was just a careless sign error. So yeah, if you did get a different answer here, Lizanne and whoever else is watching, I might well agree with you. It's a good question and it's a tough question. And yeah, it's 12 marks. It's a long question. They do ask questions like this, so once again, so it's a good one to do. This is really tough though. But like on all these questions, if you get the initial kind of like working out done correctly, then there's no reason why you can't do the whole question correctly. And you can certainly get most of the marks, if not all the marks. Now, we're told various things here. Where are we? We're told, for example, tan theta is 3/4. So, I mean, I'm just in the habit now of, as soon as I'm told that, I write down what sine theta and cos theta are. 3/5 and 4/5. That's all cool. And we need to add some forces to the diagram. Let's do all our force arrows in blue. Okay, so at the point of contact A, there's going to be a reaction, which is always perpendicular to the surface. And that reaction, I'm going to call it R1. I think in the solutions they call it N, so bear in mind my R1 is their N, but I like R1. It shows me it's a reaction force, which kind of helps. And at the point of contact, it's always perpendicular. Well, it's always forms a tangent, if you like, to the point of contact. So it actually goes off at an angle like that, this one, and this is another reaction force, and we can call it R2. Then we're going to have two frictions because both things are rough, both the hemisphere and the surface. But the nice thing is actually the mu is the same for both surfaces. So the coefficient of friction is the same for both points of contact, which is kind of nice. So we can call this one, if you like, we can call it F1, although I wouldn't stick with F1 for long. And we can call this one, which is also going to go that direction. You might be slightly confused as to why it's that direction. Think of like if you had a very smooth rod on two surfaces here, it would want to slip in this direction. It will want to slip in that direction, and so we need to put the friction going the other way. Okay, let's label those F1 and F2. But a little bit of advice here often really makes sense because F1 is simply mu R1 and F2 is simply mu R2. It's often much more convenient, and this is where I certainly agree with the approach taken in the mark scheme, just to label those mu R1 and mu R2. It's a good habit to get into that. It makes the working out slightly less bewildering because you haven't got so many letters on the page, which often you do have in these kind of situations. So we'll call this mu R1 and that one mu R2. In fact, let me give myself a bit more space to work there. Mu R2. Okay, that's all cool. Now we've also got the weight of the rod to consider. Now they said it was of length 2A, so I'm going to draw it there. I know sometimes students say, well, which side you're going to put it on. It looks, always obey the diagram as they've drawn it, and it looks like that isn't as long as this bit. So yeah, we'll draw it there. It wouldn't make any difference anyway. That's supposed to be straight down. It doesn't look like very straight down, does it? Let's have another go at that. Straight down, mg. Yeah, we'll call it mass m. Doesn't tell you that to do that, but that's always the way we deal with an unknown mass. Call it just mg. Now, there are other things we can find out about this diagram. There's definitely things we want to find out as well. I know, for example, that distance from there to there, oh, let's not do that in blue. That distance from there to there, let's do all the distances in yellow. That's A, because it's halfway along. That's no problem at all. But what about this distance up here to the point of contact? Because it's obviously going to be really useful. Now, it might look at first like we haven't got enough info to specify this distance, but actually we have, because let's call it X for the moment, very quickly, and then I'm going to rub out and get it done. And you see how most of the work goes on in the diagram initially here, so it's a good question. We can say, according to the right angle triangle we've got in there, the right angle formed by AT and, should we give that name, O, yeah? That's O. The right angle triangle ATO, we can form using the letters x, a, and the right angle there. We can come up with a tan argument. Yeah, we could say that tan theta equals opposite, which is a, divided by adjacent, which is x. Oh, but hang on, tan theta is 3/4. So I could say 3/4 is a over x, or in other words, x equals, after doing a little bit of fiddling around, 4a over 3. Vital that you realise that. So let's get rid of all the working we've done here. We can now see we've worked out x. In terms of a, it's 4a over 3. That's a much better, much more satisfying way of writing it down. So let's write it down as 4a over 3. Good, I've got that distance. That's going to be really, really useful. And then what I often also do, well, let's do this now. I like to draw my little triangles, yeah? And I'm going to think about just lefties, righties, uppies, and downies first. If I put a theta in there, that's also going to be theta. It's not so obvious from here, but it is going to be theta. And then everything's in terms of lefts, rights, ups, and downs. So I can come up with a couple of equations, and these will always be super important. The uppies equal to downies. Okay, we've got an R1 plus an R2 cos theta. That would seem to equal, plus a mu R2 sine theta. Okay, we've got that up, that up, that up, and that would seem to equal mg. Yeah, I'm not going to tidy that up at the moment. I'm not really interested in tidying it up yet. Lefties and righties. Well, here we've got R2 sine theta. That's a bit going to the left there, equals mu R1 plus mu R2 cos theta. Yeah. Now, remember, we know all the sines and coses there, so we can definitely tidy that up. But in these questions, you always end up having to take moments, but you only have to ever take them once, and it just seems sensible here to take moments at A. Yeah. Now, I'm also going to have to now resolve, because moments we resolve, I find it easier to resolve parallel to the plane and perpendicular to the plane. So if I can just draw that in there and put a theta in there, it's just going to make things slightly easier for me. I know, by the way, that I need to take another equation because there's three unknowns here. I've got an R1 which is unknown, an R2 which is unknown, and mu which is unknown. Yes, granted, I don't know the mass, but everything will be put in terms of the mass and it will cancel. Sines and coses I know, and g is a known, it's 9.8. So I need a further equation. Three unknowns, two equations isn't enough. I need one more equation. So taking the moments at A, well, we'll have the distance, which is A, times by mg cos theta. Remember to resolve perpendicular to the distance. It's distance times perpendicular component of the force. Okay, that would turn it in that direction. But then we've got these two up here, but actually the mu R2 is parallel to the slope, so that's not going to make any difference. We can just do 4a over 3 times R2. Often describe this force because it's in the same direction as the door handle. It's like pushing on a door handle from the side. It's not going to turn it. Think of it as a door handle. That will not contribute to the turning. It's only the R2 which will contribute to the turning, and the mg cos theta which will contribute to the turning. And then you just have to times them by the distances. Now, the nice thing about this equation is we can actually very quickly simplify it. So we get the a's cancelling. Cos theta was 4/5, I think. Was sine theta 3/5? I wish I hadn't written that up there. Cos theta is 4/5. And so straight away we get 4/5 mg equals 4 over 3 R2. Cross the 4's out. Times the 3 across. R2 is 3/5 mg. That's a serious result. We're cracking the problem now. Yeah. And now if I go back to these equations, I can call them, I don't know, Alice and Bob. Yeah, let's actually write these down and simplify them now. So we've got A, which is R1, plus 3/5 mg. Oh, but I'm timesing it by cos theta. Let me just write down sine is 3/5. cos is 4/5, just as a memory aid because my memory's going now and I'll forget. So I'm going to go 3/5 mg times 4/5. That's 12/25 mg. And then plus mu R2. So mu, I still want. R2 is 3/5 mg times by 3/5. So that's going to be 9/25 mg. And that equals mg. And now I'm going to do the same for B. I'm just going to simplify it, plugging in all my all the stuff that I now know. R2 sine theta, R2 is 3/5 mg, times it by 3/5 again, we get 9/25 mg, equals mu times R1, so neither of those I know, I'll just have to leave that alone for the moment, plus mu times by 3/5 mg times by 4/5, so times by 12/25 mg. And I'm just going to check my notes and check that I agree with all of that. Yeah, I think so. Yeah, perfect. Yeah. Now let me draw attention to where the mistake comes in the solutions. I think it's here. Okay, so he or she said at the start n plus r cos theta plus mu r sine theta equals mg. I completely agree with that. That I completely agree with, because n is my r1 and r is my r2, and it's the equivalent of where I wrote, if I can just move up a bit, r1 plus r2 cos theta plus mu r2 sine theta equals mg. It's the exact equivalent of that. Yeah, m plus r cos theta. You see, we're using cos theta there. Remember, r is my r2, n is my r1. Plus mu r2 sine theta, if you like, mu r2 sine theta equals mg. Yeah, so I think that's correct there. But then when he's gone to tidy it up, he's suddenly changed this magically into a minus. Yeah, why is that there? That shouldn't be there, that minus. I think it should be a plus. I've got it down as a plus, and I think that plus is right. I think that's just one of those moments where they've just had a moment where they've made a sign error. Yeah. Now, all we've got to do now, anyway, if we go back to our problem, we've noted their mistake. It would be a good idea. I didn't do. I'll show you the way I did it originally. I then plugged in because I thought, well, I've got R1. Oh, I did simplify A a little bit actually, because I was like, well, I'll take the 1225 mg over there. So I had R1 equals, take that over there, I get 13/25 mg, and then I subtracted that, which is what they didn't do, minus mu times 9 mg/25. Yeah, make sure your mu's and your m's look different. Mine look pretty similar. I'm not happy about that. Anyway, so plug into B. And then I got 9/25 mg equals mu times by 13/25 mg minus mu times by 9 mg/25. Okay, so there we go. I've used that result and I'm just plugging that result into there at the moment. That's what I'm actually doing. So now I need on the end a plus mu times 12/25 mg. Now it's annoying because if you look at it, we suddenly realize there's loads of tidying up to do. Every single term has an mg in it. So let's get rid of all the mg's. I'm crossing out both the m and the g there, yeah? Every term had an mg in it, so divide by mg if you like. Also, every term is over 25, so let's times by 25. And then we're going to have a much nicer looking equation because we've got 9 equals 13 mu, I'm going to times out those brackets, minus 9 mu squared plus 12 mu. And this is what I mean. I had a slightly different answer to them. Well, a slightly different final equation. 9 mu squared minus 25 mu plus 9 equals 0. At this point, I was, ready to, get on with the, finish the question really. So I turned to my calculator and got it to solve the quadratic. It's telling me that you end up with mu equals, we get two possible values of mu here, 2.35, or mu equals 0.425. So please, if you can see a mistake in my working, let me know. But I disagree with our answer there. I think there's two possible values of mu, and those are the two possible values of mu. I believe it comes in when, if you look at their solutions, you've got this n plus equals mg, But then when they're plugging in R, you've got M plus minus equals mg, and so that messes everything up and means that they've got a very different looking result to what I got. Because of this minus, it should be a plus, I think. So yeah, you end up with a similar but different looking, same approach, but yeah, that's it. So I hope that makes sense. I wonder if you agree with me. Let me know via email if you do agree with me. Brilliant. And yeah, keep up the hard work. Bye bye.